Okay, folks, let's see. So it's time to begin. You can see that. If you can't see that, let me know if anything's going wrong. So it looks like today's plan is we're just going to say, I just want to sort of finish up the Zeeman effect. We mostly finished it last time, but just I was rushing a little bit at the end, so I just want to finish that up. But then the main topic for today is going to be hyperfine splitting. So that's what that'll be the main event for today. So, but before we get to hyperfine, let's just sort of finish up the Zeeman effect. And so we have for the Zeeman effect, we had the idea was we have the hydrogen atom. This is how I draw a hydrogen atom. That's the 1/r potential, right? These are the energy levels. And so we have our hydrogen atom, but we put it into a B field. And so then what happens is we have a perturbation that we derived, which comes from negative mu dot B. And when we plug it all in, we see that the Zeeman Hamiltonian is going to be EB over 2m LZ plus 2SZ. Okay, and so then we talked about the strong field, which was when the Zeeman effect is way bigger than the hyperfine, the fine structure. And then we talked about the weak field, which is when the Zeeman effect is way weaker than the fine structure. And then we were sort of in the middle of talking about the intermediate. The intermediate effect strength is when the hyperfine is on the same order as the fine structure. Okay, and so this is the last regime, and this is the hardest one, because now, because what happens is, for this case, then there is no, then we have to have that H naught is just the regular hydrogen Hamiltonian, right? The hydrogen Hamiltonian for an electron in hydrogen. But then we say that H is equal to H naught plus H prime, and we ask ourselves, what is the perturbation? And so now the perturbation is the whole thing. We have to add the whole thing together. It's going to be the Zeeman effect plus the hyperfine. So I'm sorry, not hyperfine. It's going to be the fine structure. And so that means that the perturbation is going to be this big ugly mess, because I can't do any little tricks. I can't make any more approximations. I can't brush anything under the rug anymore. And so this is going to be my perturbation. It's going to be the Zeeman effect plus the fine structure. And the fine structure, you guys remember, is going to be the spin orbit, L dot S, plus the relativistic correction, which is negative p to the fourth 8 m cubed c squared. And so that's going to be the perturbation. So it's going to be the Zeeman, it's going to be the spin orbit, plus the relativistic. So they all get added together. And so that's kind of a mess. And so then we have to ask ourselves, okay, well, how does it, how does, well, let's say the question, the big question that we're always asking ourselves is, how does this affect the energy? What is the change in the energy of the nth level of the hydrogen atom? What is it? And so then we want to use, of course, perturbation theory. And so we ask ourselves the very first question, which is it degenerate? Question mark. And then, of course, the answer is yes. The nth level is 2n, it's degenerate by 2n squared. So it's massive So this, the nth level is massively degenerate. And so then the next question is, do we have a good basis? Because we can't do perturbation theory unless we have a good basis. And so there's only two bases that we know about. So one of them is our old friend psi NL M sub L M sub S. And the other one is the psi NL J MJ. So we ask ourselves, are either of these a good basis? And I think you might already start to know what the answer is, but let's just work it out. So let's look at this first one, and we see that the indices that in the quantum numbers that index this degenerate subspace is L squared, LZ, and SZ, right? And so we say, is it a good basis? And so then we start plugging. So then we have to take those guys, and to see if it's a good basis, we got to see if they commute with H prime. And so we got to plug them all into here, right? That's what we do. And then we see, does it commute? And H prime is this mess. This is our H prime. And so that goes here. And so I'm not going to go through all the details, but I think you should immediately see that it's not going to commute, because if you can find any little pieces in there that don't commute, then that's going to screw it all up, unless you get lucky and there's some magical cancellation, but that doesn't usually happen. So immediately you can see two parts in here that don't commute. Yeah, can anybody tell me? Like there's two parts in here that don't commute. I mean, I think there's many parts that don't commute, but can anyone come up with two parts? Can someone tell me two parts that don't commute? I got these three operators here, and then I got all these operators in H prime. Can anybody find anything in there that doesn't commute? Can anyone say anything?
LZ and SZ don't commute with L dot S.
Exactly. That's exactly right. Because in there, you see there's an L dot S, and then there's an S, and you see that SZ and L dot S don't commute. So immediately you see that this thing does not equal 0. And so that means that this is a bad basis. And it's a bad basis for the same reasons that it was bad for spin orbit, because spin orbit is still there. So it's still a bad. It was bad before, and it's still bad. Okay, great. Well, not great, but it is what it is. Famous words. And so then now let's consider different basis, psi N L J M J. And is this a good basis? And so let's do the same thing. So here we have the operator, the quantum numbers of this basis are enumerated by the eigenvalues of the L squared operator, the J squared operator, and the JZ operator. And so now we got to figure out the commutator of these guys, again, with H prime. And so these guys go in here. And we got to figure out all the commutators of those guys with H prime. And, you know, H prime is equal to, what the heck is it? It's the H prime Zeeman plus L dot S, spin orbit, plus negative p to the 4 divided by 8m cubed c squared. Okay, and then this one is, and H Zeeman is going to have, it's going to have some constant times LZ plus 2SZ. Okay, that's our H prime. So if we do it, we'll notice something. Like if we plug these in, we'll notice that L squared and H prime. And we actually did this when we did the weak field Zeeman. It turns out that those guys actually do commute. And when we did the weak field Zeeman, we also did JZ and H prime. And do you remember, did those guys commute?
I believe so.
Oh, hold on one second, please. Are you making that noise? Please stop. I'm in the middle of my lecture. I need you to stop, okay? Ugh. All right. So did these guys commute? Does anybody remember?
I believe they did.
Yeah, we did it last time. They commute. But this is the one that we did not do for the weak field. And this point is a little bit subtle, in my opinion. The one that we did not do for the weak field was this one, J squared H prime. And we did not do that one because for the weak field Zeeman, the J levels were split. And so the degenerate subspace only had one value of J. Whereas now, now our H naught, in this case, you have to remember, we have H equals H naught plus H prime, but our H naught now is just the regular hydrogen. And in the regular hydrogen atom, the J levels are degenerate. And so because they're not split, we have to consider the commutator of J squared with H prime. I think that's a subtle point, but it's worth thinking about, because if you can understand that, then that means you're really understanding this whole concept of this finding a good basis. So now we have to consider this commutator, which we did not consider for the weak field splitting, and I'm not going to go through all the details, but it turns out that J squared does not. There's at least one part that it does not commute with. Can anybody guess? There's one operator for sure that I know that it doesn't commute with. Does anybody know? Can anybody look at that and figure it out? You'd have to sort of have a good memory of all the commutators to get that one, I think. Let me make sure.
L.S.
Say it again?
Is it also L.S?
No, although that's a good guess. Because remember, we constructed the J basis specifically in order to commute with L.S. So it does commute with L.S, but that was a good guess. It's something else. Can anyone guess?
Is it the relativistic part?
No, because the relativistic is, remember, the relativistic really commuted with the L's and the S's. No, that's not it, but that's a good guess too. I think it's not totally obvious, but if you keep guessing, you'll find it eventually. I mean, I wouldn't have noticed it either. I think it's not completely obvious, but once you think about it, you'll realize it doesn't commute with SZ. So go play around with that and you'll see that it doesn't commute with SZ. Because J squared, well, I'm not going to go through all the algebra, but just play around with it and you'll eventually see it doesn't commute with SZ. And so that means that psi, so this doesn't equal 0 because J squared doesn't commute with SZ. And so that means that psi NLJMJ is a bad basis. Oh no! Did anybody look up Mr. Bill, by the way? Yeah, did you? Oh no! It's Mr. Sluggo! Bad basis. Okay, so yeah, it's a bad basis. Oh no! And so that means that we're screwed, basically. That means that we cannot plug into the simple formula. Cannot plug into the simple formula. Delta E is equal to psi H prime psi. Okay, we can't just plug into that simple formula. We can't just go boom and find that expectation value because the formula is no longer valid. That formula only works for a good basis. So bummer, but that means then that what we have to do is we have to construct a good basis. We have to make our own good basis. Construct a good basis. We have to make our own. You have to make it. And so And so you remember the whole point of a good basis, what the definition of a good basis is, that a good basis diagonalizes H prime, diagonalizes H prime in the degenerate subspace. That is what a good basis is. And so then all we got to do then is construct H prime and then diagonalize it. And so what is the dimension of H prime? Dimension of H prime. Because H prime is now going to be a matrix. Bum, 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 bum. It's a matrix. It's going to be a something by something matrix. What's the dimensionality of this matrix of H prime?
Is it the dimensional, like the number of degenerate states times the number of degenerate states?
That's exactly right. That's exactly right, because the whole point is that we're in the degenerate subspace. So the dimension of H prime is the dimension of the degenerate subspace. That's right. And so for the nth, so if we're in the nth manifold, the nth hydrogen energy level, how many states are in there? Somebody remind me that little number. What is the degeneracy? For the nth level? Say it again.
2n squared.
Yes, exactly. That's exactly right. 2n squared. So our matrix will be 2n squared by 2n squared. So it's going to be a big ugly matrix. And so basically we have the basis states now. We can just pick any basis we want, and we just have to pick some basis states for the degenerate subspace. And it doesn't matter whether we pick, it doesn't really matter whether we pick psi n l m sub s states, or we could pick psi n l j m j states. We could pick whichever ones we want, because we're gonna diagonalize the matrix in the end. So it doesn't matter. So just pick one. So let's just say we pick this one, and then we're gonna have the first level, the first state, the second state, the third one, up, all the way down to the 2n squared one. And so then we're going to take all of those levels, and then we're going to construct all the matrix elements. Psi 1, H prime, psi 1, psi 1, 1. It'll be psi 1, H prime, psi 2, psi 1, H prime, psi 3. We're basically going to construct. We're going to construct all the matrix elements of the perturbation. We're going to construct all those matrix elements, and so then that means that H prime is equal to H11, H12, H prime 2, 1, blah, blah, blah. We're going to construct that matrix, and then we have to diagonalize it. And then the corrections to the nth level is going to be the eigenvalues that we get by diagonalizing it. And the new states, the good basis, the new states that nature likes, is going to be the eigenstates. All right, so that's it. That's sort of how you do it. Okay, but I'm not going to actually go through that, because there's no elegant way to do it. It's just a big mess depending on which level you're looking at, which nth level. Okay, so now let's move over and do this new topic, which is hyperfine. And the hyperfine coupling is the last perturbation that we're going to discuss. The hyperfine effect is going to be the last correction. There are actually other corrections that we're not going to discuss, but this is the last one that we will discuss. It's the last sort of undergraduate level correction the last correction to the hydrogen atom, to the energy level of hydrogen. And so the idea is that now we have done this, what we've done so far is we've said, well, I have a hydrogen atom, there's a proton with a 1 over R well, I got my energy levels of hydrogen, and I can figure out what happens when I add, we added the relativistic correction, we added the spin orbit correction, we added the Zeeman correction, and in your homework you also added the Stark shift. That was, so Zeeman is a B field, and Stark was the E, is if I put an E field in there. And spin orbit, remember, was the L dot S, and the relativistic was the P to the 4. Okay, so we did all these guys. That's pretty cool. And so, but now there's one more. The last one is hyperfine. Hyperfine. And hyperfine, you can already kind of see what it means. It's like, we have the fine structure, but this is even more fine. It's so fine, it's hyperfine. So fine. Okay, so this is the last small correction, the one that we skipped, and that means that there's something missing in the Hamiltonian that we overlooked. When we did the original problem last semester, you realize that you guys overlooked a whole hell of a lot of things. You overlooked the relativistic correction, the spin orbit, the Zeeman, the Stark. You guys overlooked all that, but now it turns out that there's one last one that we overlooked. And does anybody know what it is? What does anyone know? Like and remember, whenever we talk about Hamiltonians, we always have to look at consider the classical Hamiltonian. Remember, when we're talking about energy, when we're talking about perturbations and energy corrections, we always have to find the Hamiltonian. And when we find the Hamiltonian, we always go to the classical Hamiltonian. And so if you consider the classical Hamiltonian, we have, this is the classical picture. I got an electron orbiting a proton. That's it. So classically, what have we totally forgotten? What have we missed?
Is it like some sort of coupling between the proton and the electron?
That's exactly right. Yes, it is exactly that. That's right, it is. So here's the electron. And so let's draw it a little better. The electron has spin. And so that means that it has a dipole moment. Dipole moment of electron. And the dipole moment of the electron, let's just write it. Mu E. And you guys remember there's a formula for dipoles. If I have a charged particle with a dipole, then the formula is always Q G over 2 times the mass times the spin. That's the formula. That's like what we always use. And that we sort of derive that formula because if you forget about the G factor, then that's exactly the same formula for what you can derive very trivially for an electron spinning or moving around, spinning with around. It's just this. It comes from this formula, like mu is equal to current times area, dipole. Okay, so but now we have but because it's coming from spin and we have the intrinsic angular momentum, then we have we add the G factor. Okay, so this is the formula, and so for an electron the G factor is 2 and the Q is minus E, and so we see that the electron magnetic moment is minus E over m times the spin of the electron. Okay, that's the dipole moment of the electron. But it turns out that the proton also has a dipole moment. I'll draw it right here. So this one is mu electron, but this one is mu proton. And so we have a dipole moment for the proton, and so I can write that down. Dipole moment of proton. So let's do the mu of the proton. Now it's the same formula. I just want you to understand there's nothing special here. It's the same formula. That was G of E, and so now this is the charge of the proton times the proton G factor divided by twice, and now let's do that's the electron mass, and now it's the proton mass. Okay, this is so this is because the proton is also a charged particle with spin, so it also has a dipole moment, same as the electron, same formula, just different. The constants are different. So let's write the constants in. So Q. So what's Q for a proton? Somebody tell me.
Also E.
Yeah, but now it's plus E, right?
Yeah.
It's plus, yeah. Okay, and how about, and the mass of the proton, what's the mass of the proton in terms of the mass of the electron? Does anybody remember?
It's like 1,800 times like more heavy.
Exactly, that's right. I just remember the number 2,000, yeah. It's about 2,000 times the mass of the electron. Easier number to remember. That's right. And the G factor, does anybody happen to remember the G factor for the proton? I'd be surprised if you did. I mean, I don't remember this either. I just have it written down on my notes. Does anybody know it? There's a G factor. Can you guess? All right, that's okay. You don't have to guess. 5.6. You're probably kicking yourselves. I should have known that. 5.6. The G factor is 5.6. Okay, so that's the G factor. So that then is the magnetic moment for a proton. I'll write it like this. I'll write it as plus E over 2m. I'll keep that G factor, proton, mass of the proton. But now it's this times, oh, and I forgot about the spin of the proton. This is spin of the electron, and this is going to be spin of the proton. And by the way, for an electron, we know that the magnitude of the spin is what? What's the quantum number that denotes the magnitude of the spin of an electron? What is it?
S.
Well, it's SE. Yeah, it's that. It's the eigenstate. It denotes the eigenvalue of the operator S squared. And what is it? It's almost a trick question. This is an easy question. You guys, every one of you knows the answer. But maybe the language, yeah, exactly. And maybe I'm using funny language, but I just, it's useful to use, the words, the proper words. So yeah, that's right. It's spin 1/2. So that is the eigenvalue of the S squared operator for an electron. It's spin 1/2. And maybe it's a trick question because we usually don't worry about it because it's fixed. It never changes. It's an intrinsic property of the electron. And that's why we sort of leave it out often. We ignore it often, but it's there. And so the same thing is happening for the proton. Now there's a spin of the proton. So what is the eigenvalue? What is the number associated with the eigenvalue of the S squared operator for a proton? What is it? Someone tell me.
It is also 1/2?
Yes, very good. Because protons also have spin 1/2. They have intrinsic spin 1/2. And to understand that, I guess you have to think about quarks and stuff. I mean, I don't know. That's not a topic that I know too much about. But everybody just kind of knows, spin 1/2. But if you want to understand why it's spin 1/2, you have to start thinking about what's inside of the proton, and you got quarks. But let's not worry about that. So we have spin 1/2. So there it is. Okay. So you might say, you might be tempted to say, well, look, an electron and a proton both have the same charge. It's just opposite charge. Same charge, same spin. Except one is plus, one is minus, but they got the same charge, they got the same spin. So you might be tempted to say that the dipole moment is about the same. But if you thought that, you'd be totally wrong. The G factors are pretty, one G factor is 2, one is 6, just a difference of factor of 3. That's not a big deal. Got the similar G factors. similar charge, similar spin. So you would think that, okay, they probably have the same dipole moment, or very similar, but you'd be wrong. Why?
Because of the mass?
Yeah, the mass, that's the killer. The mass of the proton is way bigger than the mass of the electron. It's 2,000 times bigger. And so that means that the mass of the proton, I'm sorry, the dipole moment of the proton is, well, is it bigger or littler than the dipole moment of the electron?
Littler.
Yeah, it's way littler. That's right. And that's why, and I will just say, that's why ESR is easier than NMR. I just will point that out. You know, if you're doing a spin resonance measurement, you know, the dipole moment of the electron, which you measured by spin resonance, and I'm not going to talk about spin resonance, but I'll just mention that you probably have heard of that, you know, electron spin resonance. That's what ESR is. And that this is nuclear magnetic resonance, NMR. The signal for ESR is much bigger. So it's bigger signal because, and this is a littler signal. Because I'm just saying, you know, measuring the nuclear, measuring the dipole moment of the nucleus is harder. It's tiny. It's a much tinier effect. Just something to remember. And it's because of this. It's because of the mass. So the mu electron over mu proton, the dipole moment's magnitude is around, you know, it's like 1,000 or something, you know. So the dipole moment of the electron is way bigger. Okay, so, all right, so we see that we have these dipole moments of the electron, and we have a dipole moment of the proton, but we still haven't answered the basic question. What is the Hamiltonian? What is the classical Hamiltonian that denotes the interaction between the proton and the electron? What is it? What is the physics of it? What is the classical Hamiltonian? Why is there an additional energy due to the coupling of the electron and the proton? Can someone explain that to me in words?
Is it like a spin-spin coupling? Like you
Yes.
want the two spins to be aligned to minimize the energy?
Yeah, that's right. But what is the classical interaction? You know, I'm saying, what is the physics, you know, like first year undergraduate physics, lower division physics? What is the classical lower division physics reason that those two spins are coupled?
Charge?
Say it again?
Charge?
No, although that's a, you know, that's a good guess, you know, because remember, charge is the reason is included in H naught, because charge is the Coulomb interaction, you know, which keeps the electron spinning around the proton. So that's what you did last semester. So you did charge already. So it's not charge. What is it?
Is it that one dipole produces a magnetic field which the other one feels?
That's exactly right. That's it. It's they live in the dipole field. But which one? Is it a mutually symmetric effect that the proton is in the dipole field of the electron and the electron is in the dipole field of the proton? Is it like this symmetric thing, or is it asymmetric? Which field do we, yeah, what were you saying?
Wouldn't it be asymmetric because the electron's dipole field is a lot stronger?
Yeah, and so you might think that's a good point. And so you might think that the electron dipole is gonna dominate, right? I mean, based on what you just said. That's right. That's a good point. You know, to be honest, I never thought of that before. I sort of set it up to be like that, but actually I never even considered that before. That's a good point. But it turns out that it's wrong. Why is it wrong? Well, I mean, that was a good point, you know, but it turns out that we can ignore the magnetic, it turns out that it's actually the magnetic field of the proton that matters. I'll draw it. And I think this is not obvious, you know, I think this is not an obvious point. That's why I like to bring it up. because I remember when I first learned this, it confused the hell out of me. So, you know, here's this dipole moment of the, you know, that's the magnetic field of a dipole moment, right? You guys have all seen it before. Maybe you even derived it in your 110 class. Okay, so there's the field, right? That's the B field, the dipole field of due to the proton's dipole. I'll call it BP for B field due to the proton. Okay, and then here's the electron living in it. Now, and that is the effect. It's the energy. It's that energy. So let's just write it down. The energy H prime is equal to the energy of the electron dipole living in the magnetic field of the proton. And so what is that energy? Somebody tell me the form. Now I want to know the formula. What's the formula? And this is a classical formula that is from lower division physics that we've already used many times in this class.
Negative m dot b.
Say it again, please.
Negative m dot b, where m is the magnetic moment.
Exactly, that's exactly right. Negative mu e dot b p. So that's the magnetic moment of the electron dotted into the magnetic field of the proton. And that's it. That is the interaction. But let's get back to that little question I raised, and the other person had mentioned that the field, the magnetic moment of the electron is like, you know, 1,000 times bigger. It's way, way bigger. And so it should dominate. And so why are we ignoring it? And in fact, you know, to be honest, I don't think I've ever even seen this issue raised. Like when you look in the books, they don't even mention this, but it always bugged me. Why do you think we can ignore the dipole? Why are we ignoring the dipole moment of the electron?
Because we're in the reference frame of the electron.
Say it again.
Because we're in the reference frame of the electron. I was also thinking like maybe the electron is like spinning in all types of directions where it's kind of like canceling out or something, and the proton is maybe like more still.
Yeah, that's the answer that's what I believe is happening. It's
Okay.
not, I don't think it's like just a reference frame thing, because then, you know, we should be able to go into the reference frame of the nucleus or the reference frame of the electron, you know. But I think it's that last thing you said. That's what I believe is the answer, is the last thing you said, which is that because the electron is moving all around, the electron, the proton is really localized at the center because it has very big mass, and the wave function of the proton is highly localized. It's living in the nucleus. So the proton is like really tiny, it's highly localized, and so it's stationary. Whereas the electron is in this extended wave function, which means that the electron is all places, is all over the place. And so the B field of the electron cancels. Cancels because the electron moves around too much. And you guys can think about that, you know, and see if you can kind of convince yourself that that's true. Okay, but because the electron is moving around, its B field is going to cancel. And what that means, it basically means that the proton will feel the up field just as much as the down field. And if you feel the up field just as much as the down field, then it cancels. And that's the deal. Okay, all right. So now we have the electron moving in the B field of the proton. And so now we have to ask ourselves, what then? So now I have a perturbation. So what is the change in the energy levels of hydrogen due to this new perturbation? Oh, okay. I have to figure that out. So let's figure it out. Let's consider the nth level. Let's just do the same reasoning. Let's consider the nth level. And then let's ask ourselves, is it degenerate?
Yeah.
And then the answer is yes. And then the next question is, of course, the good question is, do we have a good basis? Do we have a good basis? Because if we have a good basis, we're happy. We can plug into the simple formula. If we don't have a good basis, we're not as happy because then we have to do some diagonalization. So hopefully we can find a good basis. So let's check. So let's find the basis. So okay, so the basis is a little different now. It's a little different than the last problem because now it's a little different because before we were always talking about the electron, but now we have, before we had one particle, one quantum particle, the electron, but now we have two particles. And so, so now the wave function, the states, our basis states, are two particle states. And the reason is because, look, we have, this is the situation. We have the proton, but the proton has a spin, and the electron, which is, you know, circling around it, has a spin. And so this is the spin of the proton, and this is the spin of the electron. And so we have to, even though the proton is stationary, it doesn't move, but we still have to consider its wave function because it has spin. The proton has a spin wave function. So we have to say that we have the wave function of the proton. And what is that? Well, it's like a trick question. It's just the proton spin. So I'll call it SP MP. And by the way, what is SP? What is that number, SP? Somebody tell me.
1/2.
That's right. And what are the possible values of MP?
Plus or minus 1/2.
Exactly. That's right. So those are the, so how many possible wave functions are there for the proton? Tell me.
2.
Exactly. 2 states.
So I have a question. Can we get another correction by considering the uncertainty in the proton's position?
I don't know how that would work. And remember, remember, corrections come from classical interactions. So when you talk about the uncertainty in the position, that's not classical. You see what I'm saying? The interactions are always classical. So to answer your question, you'd have to ask yourself, what is the classical interaction that corresponds to the phenomena that you're describing, you know, the uncertainty in the position? And I cannot think of one. You see what I'm saying? Does that make sense?
Yeah, so would that be something that you couldn't consider with perturbation theory, or?
For perturbation theory, I need to know H prime. The first thing we do is we figure out what is H prime. And to figure out H prime, the first thing we do is go to classical mechanics. You see what I'm saying? That's the starting point. If you don't have an H prime, you don't have nothing.
Okay, yeah, that makes sense.
Okay. So, okay. So we have, but here we have an H prime. We have a nice H prime that came from, you know, classical mechanics. Our H prime here is negative mu electron dotted with the B of the proton. So, so now we have to figure out what we have the H prime. We got to see if we have a good basis. So we got the wave function of the proton, and so now we got to find the wave function of the electron. And so the wave function, so the wave function of the electron will be the spatial part times spin. Okay, because now we got to worry about spin. And so what we have then is we're going to have, so well, we've been doing this already, but the wave function of the electron is going to be psi, let's pick a basis, so n, l, m sub l, and this is our favorite basis. Let's just do this basis. All right, so let's not do the j basis, let's just do the m sub l, m sub s basis, our original basis. Remember, these guys are, you know, that's the eigenvalues of L squared, LZ, and this is SZ. Okay, so that's the states of the electron. And so now, so what I need to find is, what are the basis states of the whole system? Basis states of the whole system. What are they? What do I see the wave function of the proton, I see the wave function of the electron. So what's the wave function of the whole system? I got two particles.
Like psi1 times psi2 minus psi2, like the antisymmetric wave function.
Okay, that's a good point. Yeah, let me ask a separate question. Do we have to worry about symmetrization for this problem? Yes or no?
No,
It's two electrons. Yeah.
Why not?
because we have two distinguishable particles.
Yes, exactly. So no symmetrization because the particles are not identical. Which means then that we can just use simple product states. Simple product is okay. All right. So that means that the total wave function then will just be the wave function of the proton times the wave function of the electron. All right. So it's not so bad. So let's write down that total wave function. I know I'm being a little sloppy with my notation, but I think it should be clear what's happening. So the total wave function will be psi it's going to be psi n l m sub l m sub s, and then there's one more quantum number that really matters. Which quantum number is that?
M sub p.
Yes, because that's the only one that can change. This one is not so important, you know, the S sub p, because it's always 1/2, but it's really this one that is important, you know, the m sub p. That's right. So let's just add it right here, m sub p. And, you know, this is a way of writing the state. But really what I'm writing is, you know, another way of looking at it, I could write it like this, psi n l m sub l m sub s for the electron times sp mp. This is another way of writing it also. But I'm just writing it using this notation because this is easier notation. Okay, so that's my basis, okay? So now I could have done the J basis, right? I could have done psi n l j m j. I could have, but let's not. All right, let's just pick the simplest one to start, and the J basis is like another level of complexity. So let's just go to our original basis, the n l m sub l m sub s basis, and now I just add this new. I got this new part to it, this new proton part. Okay, so is it a good basis? All right, so we know the trick. We have to take all of these states, all of these operators, L squared, LZ, this one is SZ for the electron, and what is this one? What does that quantum number refer to? What operator is associated with that quantum number?
SC for the proton.
Yeah, that's right. So those are all the operators that define our degenerate subspace. Because all of these states, if I vary any of those quantum numbers, the energy of my system does not change. This is my degenerate subspace. Degenerate subspace. My degenerate subspace is indexed by all of those quantum numbers. So, so then to see if this is a good basis, I got to do a commutator. I got to commutate those guys with H prime, right? And then I got to see, does it equal 0? What does it equal? And I got to stick all of these guys in there, and I got to do them one after the other, right? Okay, that's our trick. That's our trick. And we're hoping that it equals 0. You know, what does it equal? Does it equal 0? We hope, because then it's a good basis. Okay, but before doing that, I have to ask, we haven't figured out what is H prime. Well, we sort of know H prime already. We know that H prime is equal to negative mu E dot B P. And we know what mu E is, because that's just going to be negative E over MS E. Okay, we know that. But what the heck is BP? We actually didn't figure that out. We haven't written down an equation for it. So we got to figure that out. So to figure that out, what we're going to use is, this is a Hamiltonian. So this is a classical object. So to figure out what that is, we got to go to the classical physics. And I want to emphasize that, you know, because we always like to put down classical physics. In quantum mechanics, we're always saying, oh, classical physics is so stupid, it's so wrong, we're so much smarter than those classical guys. But, you know, that's overstating it, because really quantum mechanics is built on top of classical physics. The classical physics is where we get the Hamiltonian from. So we always have to resort to classical physics. So classical physics is built into quantum mechanics. Okay, so let's use classical physics to figure out what that B is. And so here it is. So here I have the mu of the proton. And I know that it creates some magnetic field that looks like this, because that's what dipole fields look like. And you can derive, and there's formulas for it that you can, and I think that the way you really derive the hardcore formula is in Physics 110A. That's where you really derive the formulas. And so I have a magnetic moment, and let's put the magnetic moment at the origin. And the magnetic moment is the magnetic moment of a proton at R equals 0. And so then what is the magnetic field at R, at all positions in space? Basically, I'm asking, what is the magnetic field? What is the equation for this magnetic field? And it's a complicated equation. And do any of you guys remember it? And the answer is no, nobody remembers this formula.
Isn't it like mu over R cubed times some like dot products with the magnetic moment and R or something, but R is 0?
That's exactly right. So that is correct. But it's a hellacious hellacious formula. Let me write it down. So we'll use mu of the proton. Let's see. How do I? Okay, so this is it. This is the formula. It will be, it's mu naught, and that's mu naught is the permeability constant, 4 pi r cubed, just what you said. But then there's some messy stuff. 3 times mu p dot r hat times r hat minus mu p plus 2 mu naught over 3 times mu p delta of R. That's it. And that's a pretty ugly formula. And you might never have even seen that formula in all its glory. But this is actually this is the classical formula. And it has like these two pieces. It has this piece, and then it has this piece. And the reason it has those two pieces is because it looks like this. You have the dipole moment there, and so then the dipole is creating these curvy things, right? It's creating these curvy things, and that's the B field. It's like it goes up on this upper part, and then here on this bottom part it goes up, but then on these outer parts it's going down, see? So it's a pretty complicated object. Some parts it goes up, some parts it goes down, but in the center it's always going up, see? So that's why you have this part, which has the parts that go up and down, but this part is the center part that is always up. Do you see that? I just want you to see that. Because this, this is like, here it's down, here it's up, but here it's down. And when I say up and down, I'm talking about the B field. I'm saying B points down. Okay, so the B field is like down, up, you see it? And so that's why we have to have two parts to this formula. One part describes all that complex curvy stuff, and the other part describes that nice, simple interior B field. So, all right, so that's it. So then what we got to do is, then we have, so that means then we have the H prime, because now we have, and we know that the magnetic moment for the proton is just going to be the charge times the G factor divided by twice the mass times the spin of the proton, and so we just can plug that in, and then that gives us, and then we know that H prime is equal to negative mu E dot B of the proton, and we just plug it all in and we get our perturbation, which is this. It's an ugly formula, but it turns out to be pretty simple in the end. Mu naught G of the proton E squared over M mass of the proton, mass of the electron, times 1 over 8 pi. Then there's some messy stuff here. 3 times S of the proton dot R hat times S of the electron dot R hat minus S of the electron dot S of the proton divided by R cubed plus 1/3 S of the electron dot S of the proton times delta of R. Okay, so that's it. That is the H prime. So it's like a big ugly mess, but it's straightforward. I mean, it's just classical. Okay, it's a totally classical thing. That's that is the energy of interaction of the electron dipole moment with the magnetic field coming from the proton dipole moment. Okay, so that's classical physics. So this is a classical formula, classical. But now, okay, but now what we have to do is we have to ask ourselves, do we have a good basis? Good basis? And so that means that we have to find all these commutators from back here. So let's go back here, and we have psi n l m sub l m sub s m sub p. That's our basis. And so now, and these are L squared, LZ, SZ, SZE, SZP, And so now we have to plug those guys in to this commutator. And this goes here, and these guys go here. And I will ask you now, okay, this is a big mess, okay? But let's make it simpler. Let's just only let's look at this, and let's notice that we see the dot product is here twice. I got a dot product there, and I got a dot product here. Okay, so I got these two dot products. So let's just consider the dot product. Let's plug in the dot product there, and then look at these operators here. And let me just ask you, what is that? Is that dot product going to commute with those operators? Yes or no?
No.
Right. That's right. And you know that already from before, because you guys already did this in your homework and everything. You know it doesn't equal 0 because you guys know that S, Z, comma, L dot S doesn't equal 0, right? So you guys already know that the Z component commuting with the dot product doesn't equal 0. And so the same thing happens here, because if we take S sub Z of the electron, it's not going to commute with that. And if we took S sub Z of the proton, it also wouldn't commute for the same reasons that the spin orbit did not commute. So if that's not obvious to you, then think about it. It's just like spin orbit. It's same as the spin orbit case. It's just the same reasoning that we use to spin orbit. And so if you screw around with that, you can see that they don't commute. Okay, so therefore, it's a bad basis. Okay, but what we need is a good basis. We want a good basis. So what are we going to do? We have psi n l m sub l m sub s m sub p. And so we see that these two guys are messing us up. Mess us up. Those two guys mess us up. And so we need to convert from the bad basis to a good basis. Can anybody suggest what we do? And I'll give you a hint. We do the same thing that we did for spin orbit. It's the same thing. What do we do to turn this into a good basis?
We would have to consider the total spin.
Total spin, exactly. That's right. And so we don't need to worry about these guys because those are the spatial components. They're going to commute just fine. So we can ignore them. Like, they're going to commute just fine with this Hamiltonian. But it's these spin ones that are giving us problems. And so in the bad basis, we had these two eigenvalues for these operators, S, Z, E, and S, Z, P. And so now we're going to consider the new basis that you just mentioned, the total spin basis. So it's N sub L sub ML. We'll just ignore those guys. They're just the same. But now we're going to add the spin. So we're going to go from MS MP to what new quantum numbers? Somebody tell me.
Are we gonna do like some kind of combined spin? So like maybe like a J sub S and I don't know what the notation would be, but basically just adding those two together. And so you have the squared and then you have the Z component.
Perfect. That's exactly right. So let's call it this. Let's call it S total. Okay. That's like the J, little s total. All right. That's sort of exactly the same as the J. Comma, Now I'll just call it M sub S total. I'll put a T up there. All right. And so that's exactly right. So so now we'll do this quantum number S total, and we'll call this M sub S total. And so now this guy is going to be corresponding to the operator S total squared, and this guy is going to correspond to the operator S total. These notations can be such a pain. S total Z, where S total is equal to SE, the spin of the electron, plus the spin of the proton. Same thing we did in spin orbit, exactly the same thing. And then we can have ST squared is going to be equal to SE squared, really the same trick, plus SP squared plus 2S E dot SP. Okay, so this is the total angular momentum basis, total spin basis. So we're changing the basis to the total spin basis. Good. And so now let's test it. So let's test it. Is it a good basis? We want to test this basis. So we got to take our H prime, but our H prime, we'll just call it SE dot SP. That's our H prime. And now we're going to stick these guys. These guys we don't have to worry about because they're spatial, so they're going to commute with everything. But let's put these guys now in it. So let's try it with, so how about S total squared? Does S total squared commute with SE dot SP? Yes or no? Yes, it does, for the same reasons as the spin orbit case. And how about now SZ total? Does that commute with SE dot SP? Yes or no?
Yes.
Yes.
That's right, it does. And I mean, it's not completely obvious, you know, to do the calculation in your head, but by analogy to the spin orbit case, you should know that the mathematics is going to be the same. So when you go through all the commutators, you're going to get the same answer. It'll be 0. And so there you have it. So then that means that this is a good basis. So therefore, it's a good basis. Yay! Yay, it's a good basis. But that means I don't get to do my Mr. Bill face, but still, it's okay. Still good, even so. So, all right, it's a good basis. So that means, so therefore, we're happy because we can use the simple formula. Use simple formula. That means that delta En, I can just plug into this expectation value. I can plug in my good basis now, psi n l m sub l, not m sub s, it was s total m sub s total, h prime psi n l m sub l s total m sub s total. So we just can plug into this simple formula. So it's so nice. Okay, that's great. So let's do it. Let's do it. But let's do it only for, you see, every single state is going to have a different splitting, you know, so I can go through all of the most generic case, but let's do it, but only for the ground state. Let's do it for the hydrogen ground state. And so for the hydrogen ground state, that means that N equals what for the hydrogen ground state?
1.
L equals what?
0.
Good. M sub L equals what?
0.
Right. And so for the ground state, then we're talking about this state, psi 1, 0, 0, but we still have the spin we have now S total M sub S total, because we still have this spin stuff. And so then we want to know what is the change in energy for this. Now, this, okay, so let's calculate for this case, the ground state. So let me ask you, is this degenerate? Is it? Yes or no? Is the ground state degenerate?
Yeah, I think it can, because you can have different spins and different MSs for a certain spin.
Exactly. And now I'm going to ask you exactly how many. What is the degeneracy?
2s total. What is it? 2s total plus 1.
No, that's a degeneracy for one particle, but this is two particles.
Oh, okay.
It should be 4, because if we go back to the original product state, there are 2
Exactly.
possibilities for spin of proton electron.
Yes, 2 times 2 equals 4. That's exactly right. It's 4. But you should also remember it from this case, because remember I had SE equals 1/2, and now I'm adding it to S proton equals 1/2, and that gives me an S total. What is my S total? We've done this before. What happens when you add spin 1/2 to spin 1/2? What do you get? What are the possible total values?
0 and 1.
Exactly, 1 and 0. That's right. And how many states do we have here for S total 1? How many?
3.
Yes, we call them the triplet, and it's going to be M sub S equals 1, 0, minus 1. And how many do we have here for the 0?
1 state.
That's right. That's right. We call that one the singlet. And you guys have done this before. M sub S total equals 0. And so that's 4 states. 4 states. So you can do it either, you know, the counting is always the same, 4. So 4 states. 3 triplet and 1 singlet state. Those are my total angular momentum states. Okay, so you see that when so now when I'm talking about the ground state of hydrogen, you see that the ground state of hydrogen, when I include the spin of the nucleus, it has a degeneracy of 4. 4. All right, there's 4 states in the ground state of hydrogen. And so now, basically, when I say delta E, I'm asking you, how does this perturbation split those 4 states? That's what we're about to figure out, okay? We want to know, how does the hyperfine interaction split them? How does hyperfine split them? That's what we're about to figure out. So let's figure it out. So we see that delta E of the ground state of hydrogen is just going to be this. It's just going to be the ground state wave function psi 1, 0, 0, S total, M total S, and it's going to be H prime psi 1, 0, 0, S total, MS total. Okay, I just got to calculate this expectation value, and that's it. That tells me the answer. And I know I can use this formula because this formula is okay since I have a good basis. So now let's calculate this expectation value. And it's not too hard to do. So let's just calculate it. So I got to put in the big formula. And I'm gonna skip a step of algebra because I'm running out of time. But when we do the big formula, it's gonna look like this. We're gonna see that the thing is gonna look like this. I can write it like this: delta E ground state. I can write this as I can write it like this. You know, psi 1, 0, 0, S total, M sub S total. And so my ground, and so I can write it like this. I have U naught G E squared, that's the proton G, MP, ME, 1 over 8 pi, and it'll be like this, psi 1, 0, 0, let's just do it like this, MS, S total, MS total, and now I got this piece, which is 3 times SP dot R hat times SE dot R hat, SE dot R hat over R cubed minus SP dot SE psi 1, 0, S total, MS total. Plus, now the delta part. And the delta part is going to be 1/3 times psi 1, 0, 0, S total, MS total. And now I have the delta part, SE dot SP delta of R. Psi 1, 0, 0, S total, MS total. Okay, that's what I have. 2 parts. Because one is, remember, and they remember one came from this. I got it, the reason I have 2 parts is because one part is just comes from the curvy part, where I have up, up, down, 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 and then one part. This is the curvy part, and then one part comes from the central part. You see that? So this is the curvy part on top, curvy, and this is from the central core. So I get those 2 parts. Okay, so now there's something to notice is that the curvy part, the thing about the curvy part is I have just, I'm integrating a wave function, you know, like this is an expectation value. So you should picture this is like an integral of the wave function over this Hamiltonian. But the Hamiltonian, notice that the Hamiltonian has up parts, but it also has down parts. And so when I do this integral, I'm going to be integrating all the up parts and adding them to all the down parts. And what do you think they're going to add up to? Somebody tell me.
0.
Say it again.
0.
Yes. And I'm not going to prove that. That's actually a homework problem. That's problem number 7.31 in Griffiths, is to prove that, Griffiths. But this part is 0, okay? And intuitively, it kind of makes sense because you're just integrating over some up parts and some down parts, so it all adds up to 0. But to work out the math is a little bit of work. You got to do some work, and that's a problem in Griffiths. It's undergraduate level calculation, so you should be able to do it. But I'm not going to do it now. So now let's look at the second part, and we see now let's calculate the second part, because that's where that's the interesting part. So I have this constant. I'll just write it as a constant, but then I have this psi 1, 0, 0, the spatial part, and so now this delta function is going to go into that spatial part. But then I have the spin part, which is going to be this S total, M sub S total, SE dot SP, S total, M sub S total. And this turns out to be really easy to do, because this you could do. It's so simple, because this is really easy, because it's just going to be the integral of the 1, 0, 0 wave function with delta of R with the psi 1, 0, 0 d cubed R, and you know what that is? It's just going to be equal to psi 1, 0, 0 at 0 squared. So that's really cute. That's really nice and simple. And that's a very simple little formula. That's going to be 1 over pi a naught cubed, where a naught is the Bohr radius. All right, that's a funky little thing, h bar squared over mc squared. Okay, which is 1/2 of an angstrom, in case you don't remember. So that part is simple. But then I have this part, and the constant, of course, is simple. That we know the constant. But then I have this part, and that part is easy too, because that part, SE dot SP, is easy because you can do our little trick. We do S total squared equals SE plus SP squared is equal to SE squared plus SP squared plus 2SE dot SP. And so then I see that SE dot SP is going to be equal to 1/2 times S total squared minus SE squared minus SP squared. It's the spin orbit trick. We all love the spin orbit trick, and it will be on the test. Okay, this trick, it's like everybody loves this trick, and professors love putting it onto the test. So that means that if I do this, S total, M sub S total, and the dot product is just going to be 1/2 S total squared minus SE squared minus SP squared, S total, M sub S total. Then this thing is just going to be equal to h bar squared S times S plus 1, the total. And this guy is just going to be h bar squared times 1/2 times 1/2 plus 1. And this guy is always just going to be h bar squared times 1/2 times 1/2 plus 1. All right? And so then the formula becomes really simple. And so I'm running out of time. I don't have time to write out all the formula. But let me just write the final answer to get the delta E of the ground state is going to be equal to mu naught G proton E squared over 3 MP ME times 1 over pi A naught squared, I should say cubed, times 1/2 h bar squared, and it becomes S total times S total plus 1 minus 3/2. And that's the formula. And notice that it splits the S total states. In other words, I have 4 states, boom, 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 and this will be the triplet, and this is the singlet, and it's going to split them, and it's going to make the triplet ones go higher, and the singlet goes lower. And so this is the splitting, delta E of the triplet minus delta E for the singlet when you plug into that formula. And when you plug into that formula and you calculate that delta E over H bar, or I should say over H, you get a number. You actually get a very famous number, and that number is 1420 megahertz. Does anybody know what that corresponds to?
The 21 centimeter line.
Yes, that's the 21 centimeter line. And that's why gas clouds, cosmic gas clouds, radiate the 21 centimeter line. Because in hydrogen out in space, all the hydrogen levels are split by the hyperfine interaction, like this, and the state is constantly being excited and then falling back down and radiating 21 centimeters. Because any energy that goes into the gas cloud is going to excite those ground states, and then they will fall back down and radiate 21 centimeters. So that's where this is a big deal to astronomers. Astronomers love this. Astronomers love it because it helps them to see stuff out in space. Okay, folks, that's it. So that's where we're stopped. Sorry I went a few minutes over, but I just wanted to finish this up. Okay, guys, I'll see you later. Bye-bye. Bye-bye.